Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. It's my great pleasure to introduce Maria Paola Bonatina. She's visiting us for 5 weeks. She works for many years on automated reasoning. Today she's going to talk about how to use superposition calculus to create decision procedures. And she was very kind. In the next weeks, she's going to give informal lectures about the technical details. And if you're interested, you are welcome to come too. So,
thank you very much. So thank you, Leonardo and Tom and Nikolai, for the invitation, and thank you all for coming today and for having me here. As Leonardo said, this is the first talk where I'm going to give an overview of how one can possibly apply, at least some ways to possibly apply generic theorem proving to design decision procedures for satisfiability modulo theories problems. If there is interest in the next weeks, I'll be willing to give other talks, also more informal, just as the whiteboard, so we can discuss more freely to go into the details, if there is interest of the definition and proofs and theorems in the papers behind this presentation. So for today, this is the general overview, so we get a feeling of what has been done, of what may be investigated next. I'll start with some motivation, then I'll enumerate some of the major reasoning methods that have been studied and some of what seems to be their strengths, because different methods are good for different things and none of them is good for all. And then I'll give the overview of the results we have obtained, myself and many others, on applying generic theorem proving to satisfiability modulo theories problems that will include termination results to show that we can use what is a semi-decision procedure for first-order logic as a decision procedure for satisfiability problems. We gave a general theorem showing modularity of termination for combination of theories. Modularity means that if we have termination on each theory, we also have termination on the union. Then I shall recall some experiments we conducted actually a few years ago now with a generic theorem prover named E, the work of Stefan Schulz, on dissatisfiability problems. And then I'll overview more recent work on a decomposition approach that is meant to unite somehow the strengths of first-order theorem provers with those of SMT-solvers and try to get a little bit the best of both worlds to solve problems that are harder. And some discussion, some open discussion at the end. So let's start with some motivation. Well, we all know software is everywhere and we would like it to be reliable. It's more than a wish, it's a need. But it is a difficult goal for many reasons. Software can be artful. Software is, in many ways, a work of art. It contains the creativity, the insight, the ingenuity of people, and so that makes it difficult to treat. It can be complex. It can be huge. We all know that. It can be very varied, different pieces of software, different applications, different contexts. It can be old, and maybe it comes without documentation so that it is harder to deal with it. And even now that there are so many studies in bioinformatics, there's the possibility that software may reflect some natural, I have quotes there because natural is a heavy attribute, but still, some natural laws of computing that surface in different computing models and computing formalisms, and may also contribute to make software such an intriguing, complex, interesting, and ultimately difficult to work with work of art. Furthermore, I'm talking about software, and here we are in a software reliability research group, but we should not forget that the problems about hardware verification are not solved, and are not solved entirely at least, and the border between software and hardware is somewhat blurred. It is also evolving. It is not something defined once and for all. There is migration of functionalities from software to hardware, and there are also many approaches that actually describe hardware in such a way that it looks like software at a certain level of abstraction. So reasoning methods may contribute not only to reasoning about software, but also to reasoning about hardware. But let's stick to software. There are many approaches to software reliability. You know most of them. Most of you are experts in some of these, so you know them better than I do. There is testing with automated test case generation. There is the design of programmer assistants that enable the programmer to generate better software to begin with. There are program analyzers that analyze the programs after they have been written, or maybe during the process of developing various versions. Analysis may be static or dynamic, and they use different technologies from types to abstract interpretations. There is software model checking. We all know that model checking has obtained great results in hardware verification, but is being applied also to software. And interestingly to this talk, software model checkers make a distinguished use of theorem proving, of reasoning techniques. For instance, in bounded model checking, the problem is reduced to deciding the satisfiability of a formula. In counterexample guided abstraction refinement software model checking, theorem proving comes in because the problem of deciding whether an error in the abstract program corresponds to an error in the concrete program is formulated as a satisfiability problem. And so if we get, yes, it is satisfiable, we know that the error we found in the abstraction also appears in the concrete. If we get no unsatisfiable, then we can use the proof to refine the abstraction. And I'm leaving dots there because there is certainly more that I haven't cited. But the common notion, the common point I would like to make in this talk is that a variety of these approaches, a variety of these technologies could make use of reasoning about software. What could reasoning about software be about? It can help finding and remove bugs. It can find and remove bugs directly, less modestly. It can prove a program free of bugs of a certain kind. And more ambitious, it can prove the program correct, that is free of all bugs. Now, systems that reason about software may be varied again, but they have typically a common architecture with a front end, which is the interface where we model the program and we compile somehow the information coming from the program into formulae that can be given to the back end where we have the reasoning engine that ultimately solves the problem. So what we can think of as a theorem prover. For instance, in your group, you have the theorem prover Z3 developed by Leonardo and Nicolai, and that here would be the reasoning engine, the back end behind another system that could be your Havak or a SpecSharp or other systems in the front. The focus of this talk will be on the reasoning engine. So I'm from theorem proving. I'm going to discuss the reasoning technologies and some possibilities they make available. When we talk about automated reasoning, we usually mean two major tasks defined formally. One is theorem proving, finding a proof for a conjecture and thereby showing that it is a theorem, or else model building, building a model, which is often a counterexample for a conjecture. So let's see this a little bit more formally. We shall assume, as I said, to have some way to go from programs to formulae. So we are not concerned with that in this talk because we focus on the reasoning engine. So let us assume that is approached somewhere else. And so what we are concerned with is a reasoning engine that starts with a formula. A formula may typically have the form H implies phi, where H represents a bunch of assumptions and phi represents some conjecture. And what do we want to do? We want to determine whether this H implies phi is valid, or equivalently, whether phi is a logical consequence of H, or again, thinking refutationally, whether H union not phi is unsatisfiable. And this will be achieved by giving a refutation of H union not phi, which shows that indeed it is unsatisfiable, and therefore is a proof of the validity of H implies phi, or of the validity of phi. This is the task of theorem proving. Dually, we may have the answer that H union not phi is satisfiable, which means H implies phi is not valid. And this is done by giving a model of H union not phi, which will be therefore a counter model of phi, of the positive conjecture. And this is what is done by model building. Now, what do we have in formulae? In formulae, we have various ingredients, beginning with propositional logic, with the usual connectives and propositional variables. We shall have equality, positive or negated, with so-called uninterpreted constant symbols, ABC, and function symbol, FGH. Uninterpreted means that they are free. They could be interpreted in different ways on different structures. Then we have first-order theories, which means we restrict the attention to certain interpretations, and therefore symbols in there are not free, but they are interpreted in a certain way. They include theories of data structures, such as lists, recursive data structure that we can think of as a generalization of lists. Just like in lists, we have a constructor, cons, and two selector, car and cadre, or head and tail. In recursive data structures, we have a general constructor and, say, k selectors. Then we have arrays, records, bit vectors. We have, of course, arithmetic, because programs come with numbers, with integer or real types. And finally, we have the whole of first-order logic, which brings in the quantifier and free predicate symbols or relation symbols. Now, depending on which language, which theory we select, our validity or unsatisfiability problem or dually satisfiability problem may be decidable or semi-decidable. If we place ourselves in the general first-order logic, we shall have a semi-decidable problem, and therefore the best we can get is a semi-decision procedure. If we select the decidable fragment, we can have a decision procedure. Several of the first-order theories I mentioned before have the property that if we restrict ourselves to the quantifier-free fragment, that is, we consider only ground formulae without variables in the logical sense, we may have a decidable fragment, and therefore we can have decision procedures. In the literature, people talk about T-decision procedure for a decision procedure that decides satisfiability of a ground formula in a theory T. A ground formula without loss of generality can be reduced to a set of ground clauses. Call it S. More restrictively, people talk about T-satisfiability procedure for a decision procedure that decides satisfiability of a conjunction of ground unit clauses or a conjunction of literals, ground literals. So, what do we want these reasoning procedures to be like? We would like them to be expressive, so that they handle all ingredients, for instance, all the theories that appear in the formula. We would like them to be sound and complete, so that they give neither false negatives, saying there is no bug, not because really there is no bug, but because the proof is wrong, and giving no false positives, which means it doesn't happen. They say, yes, there is a bug, but that's not true. It's because the system could not find the proof that there is none. We want them to be efficient because each formula they will be dealing with will typically represent only a subtask of the general verification task we are after. We want them to be scalable because practical problems generate huge formulae, we would like them to produce proofs so that we can check the proof and manipulate it. For instance, remember what I mentioned before about software model checking, where one can use the proof of unsatisfiability. Okay, this is not needed now. Where one can use the proof of unsatisfiability to refine an abstraction. So being able to work on the proof is useful. And we would like them also to produce models, because as I said before, the model represents a counterexample, which is often what we are really after. We would like a counterexample that help us to find a bug. A counterexample to correctness is often a trace to find the bug. So these are all desiderata for reasoning procedures. Now, the automated reasoning fields bring to our disposal a variety of reasoning methods that are good for different things. Many of them are probably known to you and already implemented here. Let's start with the Davis-Putnam-Logemann-Loveland procedure, DPLL, which is typically used for satisfiability problems in propositional logic. And it is very strong for its ability to do case analysis, and therefore break apart large formulae distinguishing the various cases. We have congruence closure algorithm, in short CC, that are typically used to reason about ground equations. Congruence closure means, think about a graph. If we have that all the children of two vertices are in relation, then the two parent vertices having the same label are also in the relation. And we can use that to think about equality, because equality is a congruence. Then there are specialized theory solvers, for instance, the simplex method for linear arithmetic. These can be combined in the so-called DPLLT framework. That is, we have the Davis-Putnam-Logemann-Loveland procedure for propositional logic with incorporated a procedure for a theory. For instance, the congruence closure procedure for equality. EUF stands for equality with uninterpreted function symbols. Next, we can combine different theory solvers using different methods and obtain what are called DPLL-based SMT-solvers. There are different ways to do combination of theories. One is the Nelson-Oppen method. One is a delayed theory combination that essentially has the SAT solver do the combination. And model-based theory combination, which presumes that each solver builds its own model and can use it to drive the combination. But there are more. For instance, there is rewriting, also known as simplification, which brings in what into the picture? The main ingredient is that we assume a well-founded order in on terms, and therefore this gives us a notion of normal form, of an expression or a term being reduced to normal form, to a canonical form. What is important is that rewriting brings in matching, that is, the ability to match a target with a pattern in the presence of variables. So we no longer have reasoning about ground equations only as in congruence closure, but with rewriting and matching, we can work with variables. Then there is resolution. Resolution brings in the ability to deduce clauses from clauses. So it is considered a synthetic reasoning method because it synthesizes clauses from clauses. And its major point of strength is unification. If you consider resolution in propositional logic, it is not of much use. DPLL does much better. Resolution comes usefully into the picture when you go up to first-order logic, when you have universally quantified variables, because resolution enables you to instantiate quantified variables by using unification. Now, matching and E-unification can be generalized to E-matching and E-unification, which means we can do the matching or the unification operation modulo a set of equations. And this can be done also in the congruence closure algorithm to instantiate heuristically universally quantified variables using the ground equalities in the congruence closure graph as the equalities in the set E. Then we have theorem-proving methods that work by instance generation. Essentially, they implement directly the Herbrand theorem by trying to generate an unsatisfiable set of ground clauses from a given set of general clauses. Then there is the whole family of tableau-based method that, in contrast with resolution, can be seen as analytic method, because the way they work is by subgoal reduction, that is, by decomposing formulae into subformulae. And they can also be used to show unsatisfiability by so-called model elimination, viewing the tableau as a survey of all possible models and eliminating them all to obtain a proof. Now, rewriting can be combined with superposition, which is an inference rule for deducing equations from equations with variables. And this can be done in the context of so-called Knuth-Bendix completion that can be used to semi-decide problems in equational theories. And finally, when we put it all together and we put together resolution, rewriting, superposition, or some call it paramodulation, they're very similar, we get the full-fledged first-order theorem prover that can deduce clauses, of course, with equation, with universally quantified variables, from other clauses with equations. Now, this is a really large choice of tools, of reasoning methods that we can pick to build our decision procedures. Now, empirically, people have gotten to have a sense a little bit of what these various methods are good for. DPLL is good for SAT problems, especially because it can break apart large non-Horn clauses. Congruence closure is good for reasoning about ground equations. Theory solvers are very good for reasoning about special theories like linear arithmetic and bit vectors. DPLL-based SMT-solvers are very strong on ground SMT problems, uniting the strengths of all the previous ingredients. Now, when we look at the other side and we see rewriting and, for instance, Knuth-Bendix completion, these are good for reasoning about non-ground equations with universally quantified variables. Likewise, resolution is good for reasoning about non-ground first-order clauses, especially Horn. And same, when we combine resolution, paramodulation, rewriting, we get methods that are traditionally good for reasoning about general non-ground first-order logic clauses with equality. But again, these methods are not as strong as the PLL in breaking apart very large formulae, and they seem to excel especially at Horn problems. Now, this is the overview of what general theorem proving has to offer. Now let's focus a little bit more in what we are going to use in this talk. Let us assume to have an inference system for first-order logic with equality. Let's say rewrite-based, not so much because they want to exclude the others, but because all the problems you are interested in include equality, and rewriting has proved to be probably one of the best methods for dealing with equality. A tableau-based system or instance generation systems, when they want to work with equality, they also bring in some sort of rewriting and superposition. So let's assume to have one of those. An inference system is non-deterministic in nature, so in order to have a working method, a so-called theorem-proving strategy, we shall need to combine it with some control that is usually called search plan from typical terminology from AI. So we get a strategy, inference system plus search plan. And if we have a refutationally complete inference system, that is one that ensures that whenever the input is unsatisfiable, a proof can be generated, and a fair search plan, that is one that does not neglect any necessary step, and therefore ensures that if there are refutations, one can be built, we shall have altogether a complete strategy. So there are many of these. This is not our problem in this talk. We shall assume one and see what we can do with it for SMT problems. Now, the main idea of the approach I'm going to describe is the following. It's very simple. If we can show that a first-order inference system is guaranteed to terminate on any T satisfiability problem for some theory T, then any complete theorem-proving strategy based on that inference system is in itself a decision procedure. Well, it's already sound and complete because it is as a strategy for first-order logic. If we add termination, we go from having a semi-decision procedure for general first-order logic to having a decision procedure for the specific class of problems, T-satisfiability problems, where we show termination. Now, a few things to remember. If we use a generic theorem prover, we are not going to have the theory built in, so to speak, in the algorithm. So we shall give a presentation, an axiomatization of the theory, a bunch of clauses describing the theory and therefore restricting the interpretation of the symbols in the theory as part of the input. So the input will have the form T union S, where S is, say, a set of ground unit clauses, and T is a presentation of the theory. Of course, in problems, we usually have more than one theory, as we saw before. So in this approach, the combination of theories will start by giving as input a union of the presentations of all the theories we need. And also notice that the border between T and S is sort of flexible, because if someone comes with a problem that contains a formula with universally quantified variables, we can just migrate it from S to T and say that it is part of the presentation of the theory. So if you have a system where theories are built in and you have a new formula with quantifiers coming in, you have to deal with it as part of the problems. If instead you use a first-order theorem prover where everything goes into the input anyway, you can see it as part of the theory. So there is an additional flexibility there. Please.
Can you go back to the previous slide?
Sure.
So you said that the theory has to be somehow introduced as a set of axioms?
Yes.
So how does one figure out if those axioms capture the theory?
Well, for theories such as those I listed before, lists, arrays, records, and so on, such axiomatizations are known. I could give some examples if there is interest, for instance.
But I
yes.
think that is a problem that the user has to somehow solve. That is not really addressed by this theorem, right?
Yeah, that's correct. The theorem prover assumes to have, as part of the input, a description of the theory, so that will come with the problem. Yes. Other questions? No, just feel free to interrupt any time, okay? Now, what would be the advantages if we could do this? Well, we do have a sound and complete inference system, so we have complete strategies. We have advantages in terms of expressivity, because we would have the full first-order logic with equality, and in particular with native quantifier reasoning. For combination of theories, provided we can show termination, and we shall see that with the modularity result, we just give the union of the presentations as part of the input. And we have, as I said, some flexibility in drawing the line between theory and problem. Now, we can use existing theorem provers off the shelf, so to speak, or almost that way. Proof generation will be already there by default, because these inference systems typically generate a proof if they find unsatisfiable. Model generation is not as easy, but we have a starting point. If we demonstrate that the inference system is guaranteed to terminate on this T union S problem, it will terminate regardless of whether it finds a proof or not. If it finds a proof, the output will be the proof. If it doesn't find the proof, the output will be a satisfiable set, which has certain properties. We say it is saturated, and which can form the basis for building a model. because it is satisfiable and saturated, which means it contains a lot of information about what is true in that theory. Now, so far so good, but what about termination? We are starting from what is a semi-decision procedure for first-order logic with equality, so termination is by far not trivial. Here I enumerate some of our results that I'm going to outline in the second half of the talk. Termination results, we proved that a fairly standard first-order inference system is guaranteed to terminate on T-satisfiability problems in theories of data structures, and therefore it yields T-satisfiability procedures. And in some cases, when the theory allows it, this can be done with polynomial time complexity. Then I'll give a result about combination of theories, what I mentioned already before as modularity of termination. Modularity means if I have termination on T1, T2, T3, each taken separately, I also have termination on the union, on the combined problem. Then I'll give some experimental evidence, which is, however, limited to problems on ground literals, so the axioms and a conjunction of ground literals. Then I shall discuss the problem of generalizing this approach from so-called T-satisfiability problems, where we have a conjunction of ground literals, a conjunction of ground unit clauses, to more general T-decision problems, where we have a conjunction of ground clauses. And a way to do that will be by the so-called decomposition approach, which is a way to decompose the problem and then submit it to a system which works as a pipeline of a first-order prover and an SMT-solver, so that the first-order prover is invoked first to pre-process the problem and do intuitively as much theory reasoning and as much reasoning on universally quantified variables as possible, hopefully generating a ground problem, and then feed its output to the SMT-solver, an engine like your Z3, for instance, or else one can, of course, decide to pass something directly to the SMT-solver. So we have a bunch of sufficient conditions to show how to do this while preserving, of course, the satisfiability of the problem and therefore the correctness of the whole transformation. Okay, so let's go now a little bit more, second half, into the details of what we have. Termination results. We use a specific rewrite-based inference system, which is called SP from superposition. Specific, but in fact quite standard. It is one of those systems that is implemented in the most commonly used first-order theorem provers, Eve, Empire, Sparse. They all implement this kind of inference rules. So what is in there? There is resolution, there is superposition, there is factoring, there is simplification or rewriting, all very standard inference rules. Nothing terribly special or unique to this system. An important ingredient is that this inference system assumes an ordering on terms, literals, clauses. Why I mention this? I said I won't go into any technical details. Indeed, I will not. But I mention this because the ordering plays a role in the proof of termination. What kind of ordering? It is a complete simplification ordering. Complete means it is total on ground terms. If we have two terms without variables, we can always tell which is greater. Simplification ordering means it has a set of nice structural properties that are very intuitive, like a term will always be strictly greater than any of its strict subterms. That's very natural. If you have a tree, you expect it to be greater than each of its strict subtrees. And monotonicity and stability properties that are also very natural about the structure of terms and the application of substitutions. So there are many such orderings. They are implemented. They are well known. We can assume one. And most important, as a consequence of the nice properties I mentioned, these orderings are well founded. I said these orderings will be important for the proof of termination. Why? Because in order to prove termination, we shall need to prove that the inference system generates only a finite number of clauses, more precisely, that the set of clauses that persist, that is, that don't get deleted by rewriting, say, is finite. And the ordering will play a role there because it will exclude many inferences that we would otherwise do. In particular, we shall also assume that this ordering is such that T is greater than C for all ground compound terms T and constants C. This is also very natural. We can just impose a precedence where all the function symbols are greater than all constant symbols and then define an ordering recursively and get easily an ordering such as a recursive path ordering or a Knuth-Bendix ordering with that kind of property. Now, this inference system equipped with this ordering and the first search plan will give us a complete theorem proving strategy. The form of our theorems is the following. So this is not one special theorem, it's a template, a schema of a theorem. We show that a complete SP strategy is a T-satisfiability procedure. How do we show it? By showing that a complete SP strategy is guaranteed to terminate on an input given by the axioms for T and the set of ground literals on the signature of T. We proved this kind of theorem for all the theories listed here. So we have the theory of lists. We considered different presentations of the theory of lists. We can have non-empty, possibly cyclic lists. We can have possibly empty, possibly cyclic lists. The difference between non-empty and possibly empty is whether you have nil or not in the signature. Possibly cyclic means that these presentations don't include axioms to exclude models where an equation like car of x is equal to x is satisfiable. So we don't worry about cycles. We proved it for arrays with or without extensionality. Extensionality is the axiom that tells that two arrays are equal if all their locations are equal. Records with or without extensionality. Fragments of linear arithmetic, integer offsets and integer offsets modulo k. Integer offsets means the theory where you have predecessor and successor, very simple. And also general recursive data structures with one constructor and k selectors. If you take k equal 1, you get integer offsets as a subcase with the predecessor as the constructor and successor as the selector, please. Integer offsets modulo is modulo k. So you do not have all the integers, but you have only the integers from 0 to k minus 1. So it means that in integer offsets, you have actually an infinite bunch of axioms. We shall see how to deal with that say successor of x is different from x, successor of x is different from x, and so on. If you do integer offsets modulo, you pick a k, and you say successor of x is different from x, successor of x is different from x, but successor of x k times is equal to x. So you close, and you only have k values. Okay. Recursive data structures, if you pick k equal 1, you get back again integer offsets. If you pick k equal 2, you get lists. But recursive data structures usually come with axioms for saying that the structure is acyclic. That is, we can't satisfy an equation like car of x equal x. So there are acyclicity axioms there. And so we shall have acyclic lists in contrast with those I listed before. So anyway, a whole bunch of theories. Oh, here are the integer offsets that you were asking before. I mention it because this may look like an undoable problem for a theorem prover that expects a presentation as input because it's got infinitely many axioms. These are those I mentioned before. We have for all x, the successor of the predecessor of x is equal to x. For all x, the predecessor of the successor of x is equal to x. For all x and for all I greater than 0, successor of x I times is different from x. So what we do, we gave a problem reduction. Basically, we proved that it is sufficient to give as input finitely many of these axioms. How many? Essentially, it is sufficient to go up to n, where n is the number of occurrences of successor, or is, in the worst case, the number of occurrences of successor and predecessor in the set of ground unit literals. It could be simply the number of constants for which the input defines the successor. But in the worst case, if each equation introduces a new constant, it will be equal to the number of occurrences of the function symbol successor and predecessor.
You're assuming that S is grounded? That does the reduction assume that?
I'm assuming that S is a set of ground literals, yes. Big S is a set of ground literals, yes. Next, so we proved all these theorems about termination on each of these theories. Actually, they are not all that difficult because they are all based on an analysis of the inferences with respect to the theories and the ground literals, and on showing that only clauses of a certain kind can be generated under the ordering, and then there are finitely many because we have a finite signature and all the nice restriction on the inference system. But one says, well, it's not enough to prove termination for each theory. I also need to combine the theories. And what if I have to prove termination for each combination? That would be ugly. But that's not the case because we gave a modularity result. Modularity of termination means if I can prove that the strategy terminates on TI SAT problems, that is, it terminates on satisfiability problems in theory T1, in theory T2, in theory T3, each taken separately, then I can guarantee it will terminate also on the union, and therefore on any union of any of these theories. This requires two hypotheses. One is very standard for all combination methods. It requires that the theories do not share function symbols. Constants can be shared, functions not. Why is that? Well, because when we prove the modularity result, we want to prevent unleashing infinitely many steps across theories. So if we do not have a shared symbol, we prevent all the paramodulation steps from one compound term in one theory into another term in the other theory. And then we shall need to assume that the theories are variable inactive. This is a technical but very simple condition. It prevents paramodulation from variables. And it is satisfied by all equational theories without trivial models. And if you have a theory with trivial model, you can just add something like exist x, exist y, x different from y to exclude the trivial model. It is satisfied by Horn theories without trivial models. And basically with this property, we are in the realm of the so-called stably infinite theories that are also those considered by the Nelson-Oppen combination method. So it's a technical condition, but it's very simple to satisfy, and it is satisfied by all the theories we saw before. Yes?
Doesn't generalizations of the non-shared function symbols where we still have complete combination?
Yes, there has been some generalization of the Nelson-Oppen method to cases with shared function symbols. You're thinking about the work by Silvio Ghilardi.
Right. So,
yes.
Basically, there are only a finite number of saturated. Do the results lift to that?
So can we lift the modularity theorem also to those cases? I don't know yet, but it is quite possible. It's something to be investigated next, certainly. So let's see the shape of the modularity theorem. If the theories do not share function symbols and are variable inactive, and the strategy is a satisfiability procedure for each of them, then it is a procedure also for the union of the theories and therefore for any of their combinations. Now, up to this point, we were working on T-satisfiability problems. So we conducted some experiments. This was now a few years ago. So we used the systems that were available back then, version 0.82 of E and version 1 of CVC and 1.1.0 of CVC Lite. What was interesting with those experiments, at least to us, is that maybe we were a bit influenced by the SAT community. We wanted to try synthetic parametric benchmark to test scalability. We tried both satisfiable and unsatisfiable instances. We tried combination of theories, and we tried sets of literals from the Euclid system. And you see here some of the results. For instance, these benchmarks were called swap with parameter n. These are unsatisfiable instances. It was a problem, a family of problems on the theory of arrays with extensionality. It turned out to be fairly hard for those systems, at least back then. None could terminate for n greater or equal than 10. But you can see that the theorem prover, which is the one with the white circle, could do better than the systems with the theory built in, because it could take advantage of lemmata. See the satisfiable instances of the same family of problems, but they are much easier. If you look at the runtime on the y-axis, you see that these are much smaller. Anyway, the theorem prover did well here too, which is interesting because a general folklore is that theorem provers, since they aim at finding proofs, should be good at unsatisfiable problems, but maybe not so good at satisfiable problems. But once we show that the theorem prover is a decision procedure, this isn't necessarily true. This is another family of problems on arrays, where, let's see here, we have two curves overlapping, so CVC and E had essentially the same performance. On satisfiable instances, the E theorem prover did a little better. This is yet another family of parametric synthetic benchmarks in the theory of arrays, again unsatisfiable instances. And here too the theorem prover did well, and using a different ordering, the Knuth-Bendix ordering, it would do it in nearly constant time. This was the benchmark on circular Q. We modeled the Q by making up a record which has an array to hold the Q elements, and then two indices to mark the start and the end of the Q on the array, that is the first and last element of the array which is used in the Q. And here too the theorem prover could scale reasonably well with the integers modulo k. And finally, it could do very easily the problems from the Euclid set. So they were large, but all could be done in a very short time. But again, most problems are not really only T-satisfiability problems. They come with general clauses. They come with disjunctions. So we do not just have sets of ground literals, but we have sets of ground clauses. So we want to go from assuming that S is a conjunction of ground unit clauses to having S as a conjunction of ground clauses. We proved a theorem that says that if the theory is variable inactive, again, and the strategy, the SP strategy, is guaranteed to terminate on problems made of ground literals, then it will also terminate on problems made of ground clauses. This was obtained through this T decision scheme. So assume that T union S is the input, T is the theory, and S is a set of ground clauses. There is some pre-processing that involves essentially only flattening. So a subset S1 of ground unit clauses is fed together with the presentation of the theory to the theorem prover, which generates a finite limit as inf, which is then reunited with the set S2 that contains only strictly flat ground non-unit clauses that is disjunctions of equalities and inequalities between constants. Through flattening, we can essentially reduce any set of clauses to S1 union S2, where S1 is a bunch of units and S2 is a bunch of disjunctions of this kind. So we put them back together, we apply the strategy again, and we can show that this second application, if this one terminates, which we assume, this second one will terminate also, because we have an analysis of the possible inferences on clauses made of disjunctions of strictly flat equalities or disequalities, that is, again, equalities or disequalities between constants. And the theory is variable inactive, so we don't paramodulate from variables. It follows that essentially the number of paramodulation steps is bounded by the number of constants, and since we have finitely many of those, we shall have termination. Yes?
So S1 was units and S2
Yes.
was non-units.
Yes.
So you were essentially performing a completion on the left?
Yes, in some sense. These could terminate and find a satisfiability right here if it happens that only the unit part is already responsible for unsatisfiability, or else it will generate a saturated set, finite, satisfiable, saturated set. So it has in some sense compiled the part of the problem into a saturated set, which then gets reunited with the piece we left out before, and if we give it to the same strategy again, it terminates.
The SP strategy black box wouldn't do this kind of staging within.
One single run, you say? No.
It's not typical for the SP. Or good SP strategies can be guided to do this kind of ordering. First using the units, and then only once the units have been saturated, then.
Yeah, but it's not hard to do. I mean, the pre-processing of the input is not complex to implement, and then the procedure can be invoked on part, and then can restart again on the output of the first run, and the part of the input that was not yet pre-processed. So it's not hard to implement in an existing theorem prover.
It's not hard to implement, but another point is that it's not common either. It would be something that you have to do.
Well, I don't know. I mean, common is an empirical statement. I don't know whether it's common or not. It doesn't sound so uncommon to me, because you know that these kind of inference systems, ever since Knut Bendix's completion, always had a sort of double life. I mean, you can see them as a semi-decision procedure to go after a proof, or you can see them as an inference system that generates something called canonical. Now, in many cases, this second interpretation is not useful because it doesn't terminate. In most cases, saturated systems are infinite. But here, we are in a framework where we have termination to begin with. So we get a finite thing here. So it's not, it's not so unusual also from a conceptual point of view to think of these inference systems not only as proof procedures to go after a proof, but also as inference system to do a sort of completion. So this is what happens there. You can think of this as a completion, and then finding the proof in the completed set with the rest of the problem, the non-unit part. Yes?
Standard selection procedures probably don't consider that literal occurs in a unit versus in a clause.
Or you're worried about the selection strategy, about how the selection strategy in the prover could keep this quiet while working on these and activate these clauses only after this is done. But I don't think, okay, yeah, I mean, I don't think it is too hard. Okay. Other questions?
If your strategy were fair, wouldn't this happen anyway? That eventually it would saturate, and eventually you may waste a lot of time with S2.
Yes.
But you will have the same result.
indeed, earlier I thought that this was the point of the I thought that this was his question. Do it all once together? Yes, of course. This was just the way that we found easy to prove termination, so that we could reuse here all the termination results for ground unit clauses we had before, and then only prove termination from the saturated set and the flat ground disjunctions. So this is not how, and this is also probably a better answer to his question, this is not necessarily how you're supposed to implement it, because since the strategies fail, we can have the work done in one single run. This is the way we proved the termination. Sorry. So I should have answered to my first implied reading of your question, which was actually his question. Anyway. But we didn't really think about, implementing this one, because we tried a few experiments and we found that first-order provers such as E are not really thought to handle efficiently very large disjunctions, because essentially they work by resolution, and resolution tends to duplicate literals because it takes two clauses and builds a new clause by inheriting most of the literals. So if you have very large disjunctions, even with smart search plans, even with selection strategies, it gets really hard to handle those huge clauses that get generated. So we started thinking about something else, how we could somehow combine the strengths of a first-order prover with those of an SMT solver, which is based on the Davis-Putnam-Logemann-Loveland procedure, and therefore can handle the ground non-unit clauses with DPLL. So we generalized the notion of dividing unit clauses from non-unit clauses into a more general, more elegant, if you wish, decomposition principle. We take a problem and we decompose it into a so-called definitional and operational part. Definitional means we are going to have the axioms of the theory and flat ground unit clauses, for instance, that define function symbols. And the operational part will certainly contain all the non-unit clauses again. So it can boil down to what we had before, but it can also be more general. Then we shall do, indeed, theory compilation, that is an application of the theorem prover as a sort of completion engine to do as much as possible theory reasoning up front and as much as possible reasoning on non-ground equations up front. Then we shall take the output of these and whatever we left out in the original input, unite them again, and give them to an SMT solver, such as your Z3. The important thing is that we proved that in the saturated set output of the first preprocessing step, we can get rid of the axioms, which of course we want to do because the SMT solver doesn't know what to do with the axioms. It has the theories built in. So we want to show that the theorem prover can do enough completion work to have in the saturated set enough knowledge about the theory that the theory axioms are no longer needed. Essentially, we have to prove that the saturated systems, the saturated set can entail everything that could have been entailed by the theory axioms had they been still there. And so we gave a bunch of sufficient conditions to prove that this transformation preserves satisfiability. This is how it works. We call it T decision by stages. So we start with the problem, which is T, the theory, or a combination of theories, because it all leads up to combinations. S, a set of ground clauses, not necessarily unit. We decompose it. Now, the crucial part of the composition is make sure that this one only contains ground units, but doesn't have to contain them all. We can actually send some ground units here if we prefer, provided that all here are ground unit. And we put them together with the theory. and we apply SP strategy as a compiler, as a preprocessor, to generate, there I got an error in the PostScript file, so this bar should have been closer, or this S should have been closer to the bar, never mind. I didn't notice before. Anyway, we apply it to generate a saturated system, a saturated set. Then we throw out the theory axioms, which at this point we no longer need because we want to go towards an SMT solver. And what we have here, together with what we left out before, we give it to the SMT solver. And we show that this works for a bunch of theories like arrays, records, integer offsets. And in some cases, the output here is ground. So except for the axioms of the theory, the saturated output is ground, which means we actually do a reduction from the problem in the theory to a problem in the theory of equality with an interpreted function symbol. So we manage to compile away all the information about the theory, and here we get a ground set that we can just give to an SMT solver. And on the other hand, assume that we have some theory like linear arithmetic. Theorem provers are notoriously poor with arithmetic, so we prefer to give arithmetic to the SMT solver. Fine, if we have arithmetic in the problem, we just don't send anything about arithmetic to the prover. We keep it here, and we just give it directly to the SMT solver. Same for bit vectors. Bit vectors also are a theory that is handled much better by SMT solver than by general theorem provers. So whatever we don't want to bother giving to the prover, we keep it here and sending down directly to the SMT solver. Okay, we can sum it up a little bit. So what we have is a bunch of termination results to show that we can design the satisfiability procedure based on generic reasoning. We have a modularity theorem for a combination of theories. We ran some experiments. Now they are a little bit outdated, but back then they showed that the theorem prover against some folklore was not behind the then SMT solvers of the day. We generalized it to decision problems with clauses and not just literals. And one of the ways to do the generalization is this notion of decision by stages, where we pipeline the prover and the SMT solver in such a way that the prover acts as a preprocessor for the SMT solver. That is nice because you can do it once and for all and then forget about the prover and just work with the SMT solver. But it's useful especially if we have problems with quantifiers, because you can deal with those as part of the theory in the theorem prover and then not have to guess how to instantiate the universally quantified variables in the SMT solver. Some current and future work. Well, I'm looking for more termination results for more decision procedure or more powerful decision procedures, experiments with decision problems and not just satisfiability problems with literals. There is always the issue of how to find good search plans for these problems, especially keeping into account that the search plans that comes with the theorem prover we take off the shelf often are conceived for very different search problems. First order problems typically have an infinite search space, and they need narrow, deep searches to find what is often a relatively small proof in a potentially infinite search space of a semi-decidable problem. In decidable problems, often the search space and the search behavior are different. We need to be not as deep. A shallow search is sufficient, but on the other hand, we need to go wider and be more exhaustive in checking things. So there are search problems there to be investigated. Then I'm interested in integration with model building, because as I said, once you have a finite saturated set, it's a basis for building a model, but it's not yet a model as we would like it. So there are a lot of issues and problems about model representation and model extraction. Here is a bunch of references. These are 3 journal papers, one to appear, one appeared last February 2008 on the Journal of Logic and Computation, and one we just submitted it. that essentially contain all the work I served quickly here. So in there you can find all the definitions and theorems and proofs for those results. And of course I want to thank a whole bunch of people I had the pleasure to work with on these topics. Alessandro Armando, Nacho Ecenim, Silvio Ghilardi, Silvio Ranise, Michael Rusinovic, Stefan Schulz, and probably more that at least I discussed with, although they were not co-authors. And finally, I'm here for 5 weeks, as Leonardo said, and I'm looking for more friends to work with, including postdocs, students, and more problems, applications, theories to try, and things to think about. So thank you very much for your attention and for having me here. Yes?
In your last diagram, when you split the things into trying to harvest the thing from the theories, the S1, I think you said, was only unit clauses?
Yes.
So I think of the problems that I would feed to a theorem prover, they would correspond to, at the outermost level, there would be a bunch of disjunctions corresponding to the paths of the program.
Mm-hmm.
So that means I would feed it hardly any unit clause
Mm-hmm.
at all.
Mm-hmm.
So then does that mean that that technique buys me nothing? Or?
No, it doesn't mean that, because let's go back a little bit. We have to see what happens in this decomposition step. Okay, so your disjunctions will be up there in the S set. They will go first through decomposition. Decomposition will need, among other things, to flatten your problem. That is, to make sure that no term has depth greater than 1. I don't know, are your problems already very flat, or do you have nested terms?
Yeah, they're nested. I mean,
There are nested terms. Okay. So, to do the flattening, new constant symbols will be introduced, and new unit equalities will be generated to define function applications on constants as other constants, new symbols that come in to represent intermediate values, so to speak. So that this guy here will then contain disjunctions that are disjunctions of equalities or disequalities only between constants. So there you have only things like A equal B or C different than D and so on, only constants. Everything else will have gone here in the forms of unit clauses that might not have been in the original formulation of your problem, but will have been generated by the decomposition.
It's like a vocabulary.
Yes, exactly. Please.
So you can handle the unconvex theories, but you can handle literals, check satisfiability of conjunction of literals of the unconvex theory, like purely applying the superposition rules. So you never generate non-unit clauses in that process.
And?
So, well, was that that seems to be fairly different from how a solver like CDC would handle the array.
Yes, that's true. Well, you see, the issue of convexity or non-convexity, as I said, for the modularity result on termination, we assume that variable inactive thing, so we are stably infinite, but not necessarily convex. So we are more general than convex, but not more general than stably infinite for now, and we can see whether to go beyond that. But in general, let's say that that affects the modularity of termination. But in general, with the theorem prover, you don't have, in principle, restrictions. I mean, there are also, take somebody like Victor Kunkak. I mean, he was at MIT, he graduated with Martin Reinhardt, and now he's in Lausanne. He also uses generic theorem provers for reasoning about Java programs, and he doesn't even worry about termination. He just uses the prover and see how it goes, or else sets empirical limits, don't go beyond a certain depth in the proof or in the length of clauses, like you do in Z3 with SP incorporated, controlling termination by empirical means. That can always be done. So there are also people, so we worried about termination because we wanted to make the case that we can have decision procedures so that they can be embedded in something bigger and one doesn't have to worry, will it terminate, won't terminate, do I have to set a parameter to make it terminate or not. So I think that having decision procedures is important, but if you have a generic theorem prover, nothing prevents you from trying it on non-convex, non-stably infinite, non-whatever you have, and see if you can still get good enough result for your experiment, or whether you can still get termination, even if you don't have maybe the variable inductive condition.
Right. I mean, the comment was, I found it quite intriguing that you can keep doing units, resolution of units, even in the case that you have non-convex theories of combination approach, because in the deeper level problems, you'd have to start trading essentially non-unit clauses.
Well, but there will be creation of non-unit clauses in here, because say that you have the theory of arrays in here, which is not convex. So here there are the axioms of the theory of arrays, which are not unit clauses, which have universally quantified variables, and that will interact with the unit here and generate non-unit stuff, so the output will not be unit.
Oh,
okay. Okay. No, it doesn't buy us so much, the completion part, but it does buy us something. More questions or comments?